All right, today we're going to look at a technique for finding antiderivatives called integration by substitution. We have hinted at this quite a few times. I don't think I've put any on the test where you had to do anything too much with that, but we hinted at it in our differential equations worksheets where we talked about, well, you have to kind of undo the chain rule. So integration by substitution is a more formal way of undoing the chain rule in most cases, but it also allows you to do some things that you couldn't do otherwise. Okay, now because a lot of times it's just simply undoing the chain rule. Just because we're in a section on integration by substitution does not mean you have to use substitution on every problem. Okay, there will be problems where you're like, oh, I see how to undo the chain rule on that. I don't have to mess with it. Okay, but the nice thing about integration by substitution is it takes integrands that are pretty ugly looking because they're big and makes them smaller and easier to look at. Okay, so we'll do these by substitution, but I'll also show you ways of getting around that. And the thing about it is that if you don't do integration by substitution, if you can think of how to undo the chain rule, it's almost always faster. Okay, so here's the idea. Remember that if we take the derivative of sine of 3x minus 5, because of the chain rule, we start by taking the derivative of the outer function, so the derivative of sine of something is cosine of that same something, times the derivative of the inside part. Therefore, if we have the integral of 3 times cosine of 3x minus 5, well, that's what I just had here. So undoing the chain rule gets us back to sine of 3x minus 5. Notice frequently at first people are like, where did the 3 go? Well, the 3 appeared when we took the chain rule. So when we undo the chain rule, it goes back away. Okay? Now, you have to admit that looking at this whole thing can be a little overwhelming. There's just an awful lot of stuff in it, right? So one of the things that we can do is this. If G is differentiable and capital F is an antiderivative of little f, then if you have something that looks like this, f of g of x times g prime of x, so a composite function times the derivative of the inside function, then we can just take the antiderivative of the outer function, leaving the inside function alone, plus c. Okay? Now, we can make that look a little bit nicer by replacing g of x with u, taking the derivative, du would be g prime of x dx, and now I have the integral of f of u du, which is just capital F of u plus c. So by doing what some books call u substitution, we make it look a little bit nicer. So here's an example, and then we're going to do a whole bunch of examples. So here, I have the integral of a composite function, x squared plus 1 to the 5th power, times 2x dx. To use u substitution, actually I'm going to scratch this part out for the time being. Oh yeah, I have to turn this back on. I turned it off last night. Yes, Tuesday night's D&D night.
You're not drawing on your screen during
No, is a Faterum act. So I'm going to get rid of this for the time being. That is the final answer. But what you could do is this. So if I let u be equal to g of x, this inside function, x squared plus 1, and then g prime of x would be 2x, right? So du is equal to 2x dx. So I'm taking the derivative of u with respect to x, I get 2x dx. So now I have the integral of u to the 5th times du. Right? U is equal to x squared plus 1. Du is 2x dx. So the antiderivative of that is 1/6 u to the 6th plus c. And then different books say different things. I say back substitute or unsubstitute because it's kind of funny to say unsubstitute. Replace the u with x squared plus 1. So the u substitution, again, is just to make this look a little bit nicer. Now, I think many of you could look at this and go, oh, hey, look, 2x is the derivative of the inside part. I can just take the antiderivative of the outside part and go straight to this answer. And if you can, that's absolutely fine. There's nothing wrong with that. We will get to some later, not today, but we will get to some, I guess, on Friday, where that doesn't work. You can't always undo the chain rule. It used to be, honestly, that on the AP exam, every single problem that they did with u substitution, you could do by undoing the chain rule. That's no longer the case. All right, so let's look at page 2. And again, we will do each of these by u substitution first, and then we'll talk about could you have gotten there by undoing the chain rule. And the answer is going to be yes for all of these. So here, again, I will always let u be equal to the inside part of the composite function. So u is equal to x squared plus 1. Then du is going to be 2x dx. You're like, oh, that's really nice. That's exactly what I have. So now we have the integral of sine of u du. What is the integral of sine? Or the antiderivative of sine? Negative cosine. So this will be negative cosine of u plus a constant, which then we always have to get it back into terms of the variable we started in. Cosine of x squared plus 1 plus c. Okay, could you have done this just by undoing the chain rule in your head?
Yes.
Yeah, I don't think that one's super difficult. Some of them get kind of ugly because there's so many things you have to go, okay, it's not quite what I want, so I have to do some things. But that's pretty straightforward. I think you could have gone straight to the answer. Let's look at this one. First of all, what do I want to do before I even start anything else? Before that even.
Change the square root to a -2 exponent.
-2.
1/2.
Thank you. So this is equal to the integral, and I personally like to write the composite function first because then it looks more like what I would get from the chain rule. Most of the time when they're written, the problem that's given to you has the composite part last. So again, let's go ahead and do the u substitution. We'll let u be equal to the inside part of the composite function, sine of x plus 6, so that du is going to be what? Cosine of x dx. So now we have the integral of u to the 1/2 du. So that's 2/3 of u to the 3/2 plus c. And from here, it's just like, when you borrow something from somebody, you return it in the condition that it was given to you.
Theoretically.
Or better, is the idea at least. So this is 2/3 times sine of x plus 6 to the 3/2 plus c. And as always, you can, if you have the time, take the derivative of this, making sure you use the chain rule, and it should be the original integrand. If it's not, you've got it wrong. Again, I think this is one where it's easy enough to where you don't really need to do the U substitution.
Would this be a multiple choice question?
Typically, yes. Yeah, typically these are multiple choice questions.
Does it tell you to solve it by U substitution?
No. The only the only exception to that is I have seen on a multiple choice question years and years ago where they said, if you let u be equal to this and in this integral, what is the resulting integral in terms of u? So that was how at one point they made people show that they knew how to do substitution. All right, now this next one is a little bit different than the other ones. Notice I have a composite function, and I've got some other function outside, but it's not quite as nice as I'd like it to be, is it? So let's go ahead and do the u substitution. Let u be equal to x cubed minus 7. Then du will be 3x squared dx. And here's the deal. Do I want 3x squared dx? What do I actually want?
X squared.
I want x squared dx. Not a problem. How can I make this just be x squared dx?
Right, the 1/3 out to the right of the dx.
How about divide both sides of the equation by 3? So 1/3 du is equal to x squared dx. So now we have the integral of secant squared of u times 1/3, and I'll put the 1/3 in front of the integral sign, du. What is the antiderivative of secant squared?
Tangent.
Tangent. So this is 1/3 tangent of u plus c. So that's 1/3 tangent of x cubed minus 7 plus c. Now, could you undo the chain rule on this? Yes. What I would do to undo the chain rule on this is I would rewrite it as the integral of secant squared of x cubed minus 7 times, what do I really want this to be if the inside part is x cubed minus 7?
3x squared.
I really want it to be 3x squared. Well, but I've multiplied by 3. So to keep it equal to its same value, what would I have to do?
1 times 1/3.
Multiply by 1/3. Now it's set up to simply undo the chain rule. That would be 1/3. The antiderivative of secant squared is tangent. We keep the inside part. The part that was born from the chain rule goes away. Plus c. We get the same answer. But you can see you have to kind of be thinking ahead. It's like, okay, what do I really want it to be, and manipulate it. So sometimes u substitution is easier on ones like that, so you don't have to manipulate it in advance. Okay? Some people are like, I can't stand to do a u substitution if I can do it by just undoing the chain rule. Okay? I have a couple more. So here we have the integral of 2x minus 1 to what power?
1/3.
The 1/3 power dx. And at first you might think, well, that's not really a candidate for u substitution, but is it a composite function? Yeah. And what's the derivative of 2x minus 1? 2. Well, I don't have a 2 outside, but I can compensate for that, right? So I'm going to let u be equal to 2x minus 1. Then what will du be?
Well, it will be 2.
2 what?
Just 2.
Nope.
2 dx.
2 dx. Thank you.
Then you can take divided by 2.
Yeah. So then you would have 1/2 du is equal to dx. So now substituting, we've got u to the 1/3, and dx is equal to 1/2 du, so I'll put the 1/2 in front of the integral, and I'll have this. As long as whatever is outside is a constant multiple different from the derivative, you're okay. If it is something completely different, well, then you need a different technique. So now we'll take the antiderivative. That'll be 1/3 times, 3/4 of u to the 4/3 plus c is 3/8 of 2x minus 1 to the 4/3 power plus c. Again, you could do this just by undoing the chain rule. What you would need to do is rewrite this as 2x minus 1 to the 1/3 times what? What do we want out here? Nope. We want 2. So we'd have to multiply by 1/2. We just carry along the 1/2 and undo the chain rule. And you have the same answer. And you can see it's a little bit faster. But again, this is easier to look at than this, right? And at first, at least, that's the primary usage of u substitution, is to make things easier to look at. All right, last one. For this one, you're like, what the heck am I supposed to do there? Because I really have a function inside a function inside a function, right? But how can I rewrite sine cubed of 5x as something, an inside function and an outside function?
Sine of 5x cubed.
Yeah, sine of 5x, quantity cubed, times cosine of 5x dx. Again, just like we've been doing, we'll let u be equal to the inner function, sine of 5x. Then du would be times dx.
So we have divide both sides of du by 5.
Right. So we'll have 1/5 du is equal to cosine of 5x dx. So now we've got the integral of u cubed times 1/5 du. So this is 1/5 times 1/4 of u to the 4th plus c. So that's 1/20 of sine of 5x to the 4th plus c. And again, you could do the chain rule on this. You could multiply the cosine of 5x times 5 and stick a 1/5 out in front. But again, it's just a lot to look at. Okay? Any questions about that? Okay. Then your assignment's in the book.